Vamos a tener la última presentación del día. Igualmente, no debiera ser muy grande la presentación. La doctora Jo Daniel es una profesora muy conocida por muchos años en el campo de los pavimentos, de las mezclas asfálticas, de la sostenibilidad. Es profesora en la Universidad de New Hampshire y con ella pues la conocemos de su trabajo también hace muchísimos años y por eso es que la estamos invitando. Rápidamente para comentarles, la doctora Jo Daniel es profesora en el Departamento de Ingeniería Civil y Ambiental de la Universidad de New Hampshire desde el año 2001. Obtuvo su doctorado en Ingeniería Civil en la Universidad de Carolina del Norte. La investigación que ella realiza se centra en el área de materiales reciclados en mezclas asfálticas, específicamente en el agrietamiento y envejecimiento, y recientemente sobre los impactos del cambio climático en infraestructura. Actualmente es directora del Centro de Infraestructura Resiliente al Clima, UCIRC de la Universidad de New Hampshire, y es coordinadora de la Red Clima e Infraestructura ICNet. También ha participado activamente en muchos comités de investigación. Yo recuerdo cuando ella estaba de chairman en varios comités en el TRB, en el AAPT, y actualmente es editora de la Revista Internacional de Materiales para Carreteras y Diseño de Pavimentos. Nos sentimos muy honrados de tener aquí a la doctora Daniel. Por favor, recibámosla con un aplauso.
Thank you very much for the invitation to be here today, and I guess it's my job to make sure you guys stay awake for the next hour and a half to 2 hours. So hopefully I'm able to do that and at least keep you a little bit interested in asphalt for a little bit longer today. Okay, so just starting off, I wanted to give you a little bit of an introduction on the University of New Hampshire and the research group in particular. So UNH is located in New Hampshire, coastal part of New Hampshire, so we're about 5 hours north of New York and about an hour north of Boston, which is home to the 2018 World Series champions Red Sox. So any baseball fans in there in the audience? So I'm a big Red Sox fan. In any case, so we've got the UNH, and this is a picture of the main part of the campus. We're in a fairly rural location, so we've got a very nice campus, especially if you visit us in the fall time. This is a picture of our main administration building, Thompson Hall, with the clock tower, typical New England style campus, and UNH is home to the Wildcats. That's our mascot. In terms of our department, the Department of Civil and Environmental Engineering, we're within the College of Engineering and Physical Sciences. We've got 17 faculty members, and then we've got degrees at the Bachelor's, Master's of Engineering, Master of Science, and Ph.D. program. So we've got about 400 undergraduate students and about 75 graduate students. Focus areas in the department are geotechnical, environmental, materials, structures, water resources, and overarching everything in the department, and actually a focus across campus is on sustainability. Now, getting to the technical part of what we're going to talk about today, I'm going to do a little bit on the background of the intersection of infrastructure and weather to really kind of set up the way we think about things and what we're trying to look at from a global perspective in terms of the research that we conduct at UNH. And then I'm going to go into specifics on 2 projects that we've been working on in one of those areas. So we've got a lot more going on with respect to infrastructure and climate, but we'll focus just on a couple things today. So going through the intersection of weather and climate, let's think about the different aspects. So in terms of heat, we're seeing a lot of changes around the globe in terms of record-smashing heat. And that can have significant impact on various different infrastructure components, specifically thinking about what's happening in terms of railway lines buckling. A lot of instances that you're hearing more frequently where you've got aircraft getting stuck in the tarmac. There's an example of a picture of something that happened a couple years ago, so also a couple instances that happened this year. So we're dealing with increased heat, and it's not just a global average increase, but we're seeing increases in the extreme heat. So we're seeing changes in the extremes that are happening, and that can have a significant impact on a lot of our infrastructure components. Hurricanes, not something that in Costa Rica you've had to deal with, but most recently you've had a hurricane that hit the northern part of the country. The hurricanes that we're seeing more frequent hurricanes, we're seeing higher intensity hurricanes. So that's something as a community in terms of dealing with these extreme events, we're going to need to start thinking more about how do we handle these? How do we build in resiliency to our infrastructure system so that we can recover quickly after these types of events? And it's not just on the high temperature side, also on the low temperature side, especially in some areas of the country where we don't necessarily see a lot of snow or cold temperatures. There's been examples in recent years, for Atlanta, for example, a couple of years ago, where they just didn't have a good way of handling emergency response to a big ice storm. In New England, we deal a lot with snow. We can handle snow. But a couple years ago, we had average snowfalls over 3 feet more than what we're normally used to handling. And so why we can handle large storms, having large storms one after the other, that was something that we couldn't handle. It was very difficult to deal with. So it's not just specific one-time events. Sometimes it's those smaller repeated events that start to add up. And you need to figure out what are the strategies to be able to deal with those. In terms of precipitation, a lot of the areas in the United States we're seeing not just overall increases in the amount of precipitation, but what we're seeing is we're getting roughly about the same amount of precipitation annually, but we're getting it in more frequent, shorter duration storms. So we're seeing heavier, more frequent, heavier events. So that leads to a lot of different types of challenges in terms of dealing with stormwater and flooding as well. And a lot of areas around the world are also dealing with similar challenges. You can see, on a yearly basis, lots of different examples of record flooding or very unexpected flooding that's happening around the world. And again, as infrastructure engineers, we've got to figure out how we're going to deal with this. How do you design your infrastructure to be able to handle these types of events and to be able to recover from these types of events? And how do you do that? How do you figure out the adaptation? So that's in terms of weather, but then we've also got the challenge, especially in coastal areas, of rising sea levels. So this is just showing some data for the New England coastline in terms of how sea levels have been measured to be changing over time. So you can see proxy records, tidal gauge data from the last a little over 100 years, satellite data from more recently, and then the projected sea level ranges. Now, those projections have a range to them based on the different types of emission scenarios and what we think might be happening as we continue into the future. So I'm showing for coastal New England, really what they've been projecting is somewhere 1 to 4 feet of sea level rise by the end of the century, with a high of 6.6 feet. Just recently, they've been talking about how conservative those numbers actually are, and it could be 10 or more feet that we could be seeing by the end of century. Okay, so significant changes that we need to start dealing with. So in terms of the implications to future infrastructure, really we're looking at damage, okay, to those infrastructure components from the heat, from wind, from flooding, wave damage when you're talking about the coast. In terms of overall day-to-day changes, expecting increased operation and maintenance costs, and overall increase of not just component failure, but system failure. Okay? And again, being able to build in those redundancies, come at it with an adaptation approach, a holistic look at looking at making sure we're preparing and being flexible for what future conditions could be. So in that respect, at UNH, we've been working to try to get folks around this idea. So about 6 years ago, we formed the Infrastructure and Climate Network, or ICNet. And this is a collaborative network of over 75 climate scientists and transportation engineers in the Northeast. Okay, so what we've done is brought together engineers, scientists, agency folks, okay, from the region to really look at what are the challenges that we're facing and how do we deal with this problem. And it's not just about the infrastructure engineers being able to adapt to certain climate information, but really understanding what is the variability, what's the uncertainty in some of those climate projections, and how should we best use them in the engineering design. And then on the flip side, getting the climate scientists to understand what is it that engineers use or need from the climate output. Okay, so there's a lot of communication that's happened, a lot of networking, and really what we've been able to do is accelerate some new research and adaptation in climate change impacts across the Northeast with respect to transportation infrastructure. So that's the network side of things. At UNH, we've also established the UNH Center for Infrastructure Resilience to Climate. So this is the research arm where we're really looking at developing those new methods and approaches to not just the engineering perspective, but also from the planning side, okay, operation and maintenance, and then also looking at the public policy, okay, because we are mostly public-funded transportation infrastructure. You've got to have that public policy piece that comes into play if you're talking about making change at that level. Okay, so let's talk a little bit more specifics about some of the projects. So I'm going to start off with something that's probably fairly familiar and comfortable for most of you in terms of asphalt mixtures. And then the second one that I'll talk about will be probably a little bit different. We'll be talking about the impacts of sea level rise on pavement performance. So going into performance evaluation, looking at viscoelastic and fracture properties of both plant and laboratory produced asphalt mixtures, specifically looking at how those materials age with time. Okay, so we're looking at making sure that we can predict and project what the performance of those materials are going to be over their entire lifespan. So most of what I'm going to present today is the result of two projects that we've worked on with the New Hampshire DOT. The first one finished about 2 years ago and really looked at the correlation between laboratory and plant-produced mixtures with high recycled content. So New Hampshire DOT had been using recycled materials, mostly RAP, for about 25 years. And their question was really looking at, is it better, or how can we look at the difference between what we do at the mix design stage in terms of the laboratory produced materials and what the plant produces. So are we doing things in the laboratory appropriately to accurately represent what's happening to the materials as they go through the plant? Okay? And looking at this from the perspective of recycled mixtures. The second project is one that's currently ongoing, so I'll present the results to date, but that one is following on from that first project, looking at, okay, now that we have a better understanding of how this works, what is the appropriate approach for conditioning these materials in the laboratory to accurately represent what's happening in New Hampshire, okay, looking at various types of materials. Okay, so a little bit about the laboratory aging that we're using for these projects. For the short-term aging condition, we're looking at plant production. Okay, so when we did the laboratory versus the plant, we've got the laboratory-generated specimens and then that are short-term oven-aged, and then comparing them to those materials that are coming directly out of a plant. For the second project, for the long-term aging conditions, we looked at several different approaches that have been proposed recently in terms of representing aging that happens in the field over time. So we looked at 5 days at 85 degrees C for compacted samples, which is the current recommendation through AASHTO R30. We're looking at both the 5 and 12-day 95 degrees C on the loose mix, which is coming out of the NCHRP 954 project that was recently completed. And then we also looked at 24 hours, 135 degrees aging on the loose mix that was coming out of Asphalt Institute recommendations. So we wanted to evaluate these different approaches to see if there's similarities or differences in terms of the properties that we're measuring. In terms of testing that we've conducted, we're looking at both binder testing and mixture testing. Most of the binder testing was extracted and recovered from the mixtures, In the cases where we were able to get the tank material from the plant, we also did the testing on the tank asphalt as well, mostly looking at PG grading, so going through the typical PG grading protocol with the DSR and the bending beam rheometer. And then more recently, we've been looking at using the 4mm DSR protocol to be able to fully characterize the material over a wide range of temperatures and not have to do the BBR testing. For mixture testing, we're looking at complex modulus to establish the viscoelastic or the rheological properties of the material, and then also looking at the simplified viscoelastic continuum damage approach for direct tension cyclic fatigue testing, the disc-shaped compact tension test for looking at low temperature fracture, and the semicircular bend test for looking at intermediate term temperature fracture parameters. Okay, and those, again, we're focusing on cracking because that's the primary concern in New Hampshire. A little bit more detail on the binder testing. PG grading, I think everybody's familiar with. The other parameter that we've been looking at for the binder side of things is the delta TCR value. So it's the difference in the temperature at which it meets the BBR stiffness criteria of 300 megapascal and the temperature at which the material meets the low temperature slope, or M value, which is 0.3. So the difference between those two temperatures, okay, and it's been established through the literature from work that was done at Asphalt Institute that if that value is above negative 2.5, okay, that's an indication that there might be concern for some cracking. If it's above negative 5, that's more of a warning limit. Okay, so we're using those relative thresholds to evaluate the different binders. Okay, but it's really looking at this parameter, looking at the stiffness versus the relaxation capacity. And as that delta TCR becomes more negative, really what that's indicating is you're losing the relaxation capacity, which means you're more prone to cracking. In terms of the mixture testing parameters, okay, for complex modulus, again, similar to complex modulus for binders, we're looking at stiffness and phase angle. And then for the direct tension cyclic fatigue, for the SVCD approach, okay, there's a couple different parameters that we're looking at. One is the average dissipated pseudostrain energy and looking at how that's changing with the number of cycles to failure. And then more recently, we've moved to the newer protocol or newer parameter that they've identified, which is the average reduction in pseudostiffness up to failure. Okay, so if you're looking at the GR parameter, higher number of cycles to failure, at a GR value of 100 is preferred. And for the DR parameter, just remember that the higher that DR value is, the more resistant your material is predicted to be to cracking. For the disc-shaped compact tension test, okay, we're following the standard protocols, the ASTM standard, okay, and the testing is done at 10 degrees above the low temperature at which the material is expected to be placed in the field. So that test is conducted at different temperatures depending on the location that the material is going to be in the field. Okay, and the parameter that we're looking at there is what's called the fracture strain tolerance. Okay, so the fracture strain tolerance takes the work, okay, or basically the area under your curve. If you look at the load displacement curve, which is then normalized by your fracture surface area, and then that normalizes that value by the fracture strength. Okay, so looking at that peak value that you're seeing in terms of the load. The semicircular bend test, similar type of response that you get in terms of the test results, looking at the load versus displacement curve. In this case, we're using the Illinois approach in terms of calculating the flexibility index, which is, again, the area under that curve, your load displacement curve normalized by your fracture surface area, and then normalized by the slope at the inflection point. So it's really looking at trying to differentiate between materials that have a more brittle fracture versus a more ductile fracture. Okay, so those are the parameters that we're using. Okay, starting into some of the results from the first DOT test, looking at that correlation between those laboratory and plant-produced mixtures. Okay, this study incorporated 11 different mixtures, Okay, looking at production that was happening at 2 different plants, recognizing that different plants will operate differently. Looking at various binder types, so we've got a range of the most common binders, PG grade binders that are used in New Hampshire. Also looked at the impact of binder source, recognizing that if we're looking at aging and if we're looking at what's happening in the lab versus what's in the plant, the source of the binder could have a significant difference because of the differences in chemistry. Okay, so we looked at several different binder sources for some of these, different aggregate gradations, okay, relatively fine to relatively coarse mixtures, and then looked at different recycled material components. So from 20% wrap by total weight of the mix up to 30%, and then also 20% combination of recycled asphalt pavement and recycled shingles. Now, this is the first time that New Hampshire DOT had actually produced mixture and put it down in a state project with shingles. So this was kind of a big deal. All right, let's get into some of the binder results. So we'll start by looking at the performance grades, and this is the high temperature PG grade. What I'm showing on the figure right now, these are the tank asphalts. Okay, so we've got 4 tank asphalts that we're looking at, 2 PG 58 minus 28s, 2 different sources there, and then 2 PG 52 minus 34, again, 2 different sources. Okay, and then you can also see the PG high temperature grade for the wrap source that was used. The shingles that were used in this project were too stiff to be graded, so we don't have that information. Or I should say, too stiff to be graded with the equipment that New Hampshire DOT or any of the contractors had, so we couldn't do that. Okay, now looking at the extracted and recovered binder results. So what I'm showing here is the results from the 12.5 millimeter mixtures. The bars that are in red, those are the laboratory produced mixtures. The bars that are in blue, those are the plant produced mixtures. So again, the difference between the two, the laboratory produced mixtures, those were all mixed and compacted in the laboratory setting. Plant-produced mixtures were sampled after plant production, and then the extractions and recoveries done. When we fabricated the laboratory specimens, we replicated the plant-produced gradation. So it wasn't the mixed design gradation, it was the plant-produced gradation. Okay, so we replicated what the plant actually produced as close as possible. Okay, so really what we're trying to do is isolate the differences in the conditioning that each of the different types of mixtures experienced. So you can see the 2 different binder sources. So we've got the McAsphalt, the first source, and the PG 58 minus 28 and the 52 minus 34. Okay, and so you can see the variation in terms of the wrap content. Okay, so as we've got higher wrap contents, you can see a little bit of an increase. Okay, not so much with the with the laboratory produced materials, but you do see the increase with the plant-produced materials. Okay, also with respect to the addition of the shingles, you really see the difference between the 30% or the 20% recycled material component when you've got a portion of that coming from the shingles. It's a lot stiffer. Okay, the other thing that you'll notice when you're comparing the lab to the plant, typically for these materials, the laboratory-produced materials were not much stiffer, but were stiffer than the plant-produced materials. Looking at the results from the 19 millimeter mixtures, okay, here we've got a couple different sources. And again, we're seeing kind of the same thing. Okay, differences with the wrap to the wrap RAS materials, a little bit of a change with the different content for just the wrap, but still we're seeing stiffer response from those laboratory-produced mixtures than from the plant-produced mixtures. Okay, so that's on the high temperature side. Similar graph except for on the low temperature side. Okay, and so these are laid out in the same order. Okay, you can see one thing to point out, when we did test the tank asphalts, okay, whoops, the PG 34s, minus 34s, didn't quite make the minus 34 grade, okay, when we actually tested them in the lab. Okay, they were supposed to be minus 34s, didn't turn out to be quite minus 34s, so they were borderline to start off with. In terms of the wrap, you can see New England, we don't have super stiff wrap, so if you noticed on the high side it was an 82. Okay, on the low side we're looking, I think it was around a minus 18. But if you look at the response of The mixtures, again, we're seeing similar kinds of things that we saw on the high side, okay, in terms of the changes with the different recycled material type and content, okay, and also the differences between the laboratory and the plant. Okay, we're seeing a lot or more of a change or warmer temperatures with the laboratory-produced mixtures than with the plant-produced mixtures. Okay, and actually, the other thing to point out, I wanted to point out with these mixtures is these Suncor materials. Okay, those seem to be the worst, okay, in terms of the amount of change from what the grade should be. Okay, for both the laboratory and the plant-produced mixtures. Okay, and this is where it really shows up. So this is the delta TC value. You can see for the Avery Lane and the 2 McAsphalt virgin binders, okay, those are pretty good in terms of starting off with for the tank binders. Okay, the 1 McAsphalt, the 52-34, that's a little bit closer to our crack warning line. Okay, but our Avery Lane and McAsphalt, those are actually fairly good. Okay, the one that does stand out is that Suncor. Okay, that Suncor binder did, as the virgin binder itself, if you looked at the delta TCR, identified itself as being a problematic material. Okay, turns out that that material did have REOB in it. Okay, not a surprise after we actually went through the testing. So REOB is, I don't know, do you guys deal with REOB? Not so much. Okay, so just a quick explanation. REOB is recycled engine oil bottom. So essentially when motor oil is recycled, okay, and that's refined and used, the residual that's left over at the end can be used or has been used relatively frequently, depending on the area of the country, as an additive to asphalt binders, specifically some of the softer binders, to get them to meet the PG grade. Okay, and that was identified, I don't know, about 10 years ago as potentially problematic. So a lot of work went into identifying the presence of this material, which is relatively easy to fingerprint because of the heavy metals that end up in the material. But what it's shown to do is when it ages, okay, so it'll meet the requirements in terms of the PG grading, but then when you look at how that material ages, and also when you look at something like the delta TCR, you're losing that relaxation capacity relatively quickly with that material. So those tend to be materials that you observe relatively early in the life cracking issues with. Okay? And we have seen that in the field as well with some of the field mixtures. Those materials that have been shown to have the REOB at certain percentages did show earlier cracking in the field as compared to other materials. Okay? And again, you can really see it with those Suncor materials, how high those delta TCR values became. Okay? And again, we're seeing differences between the lab and the plant. In this case, the lab aging didn't have a significant impact on the delta TCR as the plant aging. Okay, so they're different in terms of the PG grades versus where you're seeing the differences in the stiffness and the relaxation capacity. So that was important to note. So those are the binder results. Now, because we're dealing with mixtures, we wanted to look at the mixture performance as well. Okay, so this is just an example of some of the dynamic modulus curves, okay, with the plant versus the laboratory. The plant curves are those in blue. Okay, the laboratory produced materials are in red. And you can see for some of the mixtures, there was a relatively big difference. Okay, and this was a statistically significant difference. Okay, so that means whether if you're looking at these materials and you're putting these materials into some type of performance prediction model, okay, that could have a significant impact on the level of distress that you predict, okay, because of how you actually fabricated the specimen and the protocol that you used to do that. For some mixtures, it didn't matter. Okay, and so really what came out of this project was an it depends answer. Okay, there wasn't a consistent trend in terms of different types of recycled materials, different types of binders, grade or source. Okay, so this is what led into the next project of really okay, so we're not going to be able to, specifically say, if you do this in the lab versus you do this in the plant, okay, there's a specific offset that happens. Really what we need to do is then focus on what's happening in the field and how do we most appropriately simulate that in the laboratory so we've got the best possible information for what's going to be happening in the lab. And so that led into the next project. Okay, it was really looking at aging and how that impacts our cracking performance of mixtures. Okay, so DOT at the end of this project, we should have a protocol for New Hampshire DOT to start to implement at the mix design stage to condition the materials to be able to predict more accurately what the performance is going to be in the field over time. So this project, we used some of the same mixtures. Also, I should note that as a result of this first project, there's some issues with the shingles mixtures and with some of the other results that we've got. So New Hampshire DOT, those were the first and last shingles mixtures that were put down in the state, okay, for a state project. So moving on to this next project, we're focusing on surface mixtures, okay, because we're looking at aging, so we're most concerned with those surface mixtures, at least initially. So we used our surface mixtures that just had recycled asphalt pavement, just the wrap from that initial project, okay, because we do have field sections that we can look at over time, and then added some more common mixtures that are used in the state. Okay, so you can see we've got, again, a range of asphalt binders. Okay, in this project, we added different design gyration levels, okay, so different types of mixtures for different tiers of roadways, more of the 12.5 and 9.5 millimeter mixtures, okay, again, and then a range of recycled binder contents. We also included a couple virgin mixtures and a couple of the specialty mixtures that New Hampshire DOT is using a lot more for some of the specific applications. So we've got a 70-34 and also a 76-28, okay, and these are polymer modified materials. Okay, so just a couple of examples. So I'm going to go through some sample plots here, and these are for one representative mix. I'm not going to show you the results from all of the mix because the general conclusions and the general trends that we saw for all the mixtures were very similar. So the data that you're going to see is from the, one of the PG52-34 mixtures. It was a 12.5 millimeter, 30% wrap. So you can see here in these plots, we've got the dynamic modulus and the phase angle master curves. Okay, and you can see the short-term age. So again, these are all plant-produced mixtures. I should say these are not laboratory-produced mixtures. For this part of the project, it was all plant-produced mixtures. So the short-term condition, which is the black dots, okay, those were the mixtures that were sampled right out of the plant. Okay, so they were reheated for the purposes of fabricating specimens, but no additional conditioning was done. And then the blue X's, okay, those are the materials that were compacted and then aged in a compacted state for 5 days. Then we've got the yellow points. Those were the 5 days of aging in the loose condition at 95 degrees C, which were then compacted. And then the red is the 12 days at 95 degrees C in the loose condition, and then the green is the 24-hour at 135 degrees C in the loose condition. So for the dynamic modulus curves, you can see not unexpectedly, as you increase the aging level or increase the amount of laboratory conditioning that's done, you've got an increase in stiffness. Okay, and we did see that the 5 days aging compacted and the 5 days loose, okay, very similar results in terms of the stiffness. Okay, statistically speaking, we couldn't say that there was a difference between those two. Also interesting that the 12 days at 95 degrees C, okay, were statistically similar to the 24 hours at 135. Okay, and again, this was for that whole range of mixtures that we tested. Okay. So we're pretty confident in those two aging protocols, just for whatever reason, they happen to do this, basically produce the same level of change in the mixtures with respect to our dynamic modulus and our phase angle. So the viscoelastic characterization, okay, in terms of those aging protocols is the same. For the phase angle curves, you can see as the aging level increases, not only does the peak phase angle decrease, it also shifts to a lower frequency. Okay, so that's important when you're talking about the relaxation capacity of those materials. Okay, it happens at a different frequency, okay, and also you're seeing that decrease. Okay, you can also, so we looked at these individually, you can also look at these in black space, okay, which is really plotting, cross-plotting the stiffness with the phase angle. Okay, so that gives you a little bit of a different picture where you can look at the combined effects of the stiffness and that relaxation capacity. Okay, again, you're seeing the same thing, okay, where you're seeing a decrease in your phase angle and the shift in where that peak occurs, okay, as well as an increased stiffness, okay, with the different aging. Okay, so it's just a different way of looking at it. Okay, you can also look at the impact of the aging as a function of how it changes, or the different long-term aging protocols as how they change from the short-term aging condition. So what this figure is showing is the dynamic modulus, or the stiffness, from the short-term aging condition on the horizontal axis, and the stiffness at each long-term aging condition on the vertical axis. So you can see at the low frequencies and at the high frequencies, okay, so the low frequencies are on the lower left, high frequency on the upper right, okay, there's not as much difference between, in terms of, not as much impact of the aging conditions, the longer term aging protocols, okay, in terms of changing the stiffness. When you get into those mid-range frequencies, you can see changes in stiffness of 2, 3, or 4 or more times in terms of the change in the stiffness. Okay, so really where we're seeing that change, okay, in the rheology is in those mid-frequencies, okay, which really is typically where we're seeing most of the range of in performance in the field. So it is something that we need to pay attention to. Doing the same thing for the phase angle, okay, looking at how that phase angle changes with aging with respect to the short-term condition. Okay, again, you can see as we've got, looking at those high and intermediate frequencies, okay, you've got lower relaxation capacity and then higher relaxation capacity at the lower frequencies as we increase the long-term aging. Okay, so again, important to kind of understand how those different things are changing as the material is conditioned, or as it is aged. Now, the other thing that we were able to do, because we had those materials that were placed in the field, okay, from the original project, we were able to go out and get cores in the second project once the materials had been in place in the field, experiencing actual field aging conditions for about 4 years worth of time. And obviously, as we continue the project, we're going to continue to do this, but this is the first set of data. Same mixture here, looking at the results of the field core testing, and again, focusing on the surface mixture. Those mixtures that had been out in the field for about 4 years, when we look at the viscoelastic characterization at the end of that time, they're roughly equivalent to that 5 days of aging. So that was interesting to see that 5 days at the 95 degrees C roughly simulated what those mixtures were experiencing in New Hampshire conditions over the first 4 years of their life, okay, with respect to both the dynamic modulus and the phase angle. So what we did was took this a little bit further with some of the results or some of the work that was done in the NCHRP 954 project to look at what were the appropriate aging durations, okay, at that 95 degrees C that best reflect the time and conditions at particular locations across the United States. So they developed what they called a climate aging index. So we applied that to our conditions to see really, okay, with this climate aging index, what is the appropriate depth, or what depth are we really simulating? Okay, so we know the time because we've got the cores from 4 years, but really what's that reflecting in terms of the depth according to this model that they developed and calibrated. It's a national calibration, but at least looking at comparatively where do we fall. So looking at this for the 5 days at aging, okay, it looks like the appropriate depth that we're simulating is 4.3 millimeters, okay, in terms of depth from the surface. And then the 12 days is simulating 9.6 years. So again, that's what we're trying to do, is based on that 4 years, establish what the depth is, okay, and then based on that same depth, okay, if we're doing 5 days and then 12 days, what is that 12 days, relatively speaking, doing, okay, in terms of the time in the field? Okay, so then we've got some kind of feel for, all right, 5 days is giving us 4 years. If we do 12 days, that gets us a little bit more than double the time in the field. And again, we're going to continue to evaluate this over time. So now let's jump into some of the mixed testing results. So we'll start with the fatigue results. So again, this DR parameter, all you need to really remember for this project or for the presentation is the higher the number, the better. So we're looking for higher values. Okay, and the way these plots are set up, we've got the individual mixtures along the bottom, and then we've got the short-term condition is purple, then 5 days is blue, 12 days is red, and the 24-hour condition is green. Okay? And you'll notice that we don't have all of the conditions for all of the different mixtures. At this point, okay, we started to be a little bit more efficient about which mixtures were tested under which conditions. Okay? And some of the early mixtures, we didn't have any more short-term or more plant material to test in this particular project. So so that's the top figure, and the bottom figure, what we're doing is looking at the ratio between the long-term age condition and the short-term age condition. Okay, so looking at how much or what percentage change or loss do we see with those longer-term aging levels, okay, and how is that different from mix to mix? So you can see, in general, we're seeing a decrease in that DR value, okay, with aging, not unexpected, right? What we'd anticipate happening as the material ages, it becomes more susceptible to cracking. Okay, now the one thing that is interesting here is, remember when we were looking at the viscoelastic material response, the 12 days and the 24 hours were pretty much the same, and they were statistically the same for that viscoelastic response. When we start looking at the fatigue response, that's no longer true. Okay, so when we start to look at a test that actually produces damage in the material, we're seeing a difference in the response from those two different aging protocols. Okay, and it's not necessarily consistent. Okay, it's not always one is greater than the other. Okay, sometimes for some mixtures, they're pretty similar. Okay, for some of the mixtures that we've evaluated, one is more severe in terms of the change in the parameter value than the other. Okay, and so that's something that's important to realize. Okay, even if an aging protocol shows you the same thing in terms of the viscoelastic response, when you get to the point of looking at what's happening during damage, okay, it can change. It can be different. The other thing that we started to notice was that for a lot of the mixtures with the typical New Hampshire binders, so those PG 58s, 52s, minus 28, minus 34s, okay, we're seeing similar ratios. Okay, but then when we looked at those two specialty materials, okay, the highly polymer modified materials, the 7034 and the 76 minus 28, we're seeing a difference in behavior. Okay, so it seems like these tests or these evaluations were able to separate more traditional binders from those polymer modified binders. Okay, and one thing with the polymer modified binders, and you'll see this in some of the other results, okay, they do tend to have a bigger drop, okay, or more of a change with aging than some of the other materials. But it's not just important to look at that, but also recognize that even if they have a larger drop, once they're aged, those values still are better than some of those traditional materials. Okay, so they can age more rapidly, okay, or change more rapidly under aging conditions, but even under the similar aging conditions, they still might be better in the end. So you've got to look at both things. Okay, so in terms of fatigue, the SVCD fatigue approach, the fatigue testing is also linked with a pavement evaluation. Okay, and I know John alluded to this. I walked in just in time to get this link back to yours in the morning. Especially when you're looking at fatigue, it's not just the property of the mixture. Okay, you've got to think about where that mixture is going to be placed in the pavement structure. Okay, so one of the things with the fatigue performance, okay, is what we've done is taken the results from the mixture testing, combine that with the viscoelastic response, okay, and a pavement evaluation, so actually putting it into a pavement structure, okay, and predict what the performance is going to be over time. And that can completely change things. Okay, so you might get one picture looking at the fatigue characteristic from a laboratory test and say, okay, yeah, this mixture is better than the other. But then once you put it into a performance model and really look at how that material is going to perform in a pavement structure, you can get a completely different picture. And this is just an example here. What I'm showing in this figure here on the right, figure on the left is some of the fatigue curves, the characterization that comes out of the test results. But really what I want you to focus on is this figure on the right, which is looking at damage over time for the different conditions. And you can see, okay, with the particular pavement structure that we used in this evaluation, that short-term age material shows to be the worst. Seems to not make sense really initially, right? Okay, but then if you think about what's happening as the materials are aging, if you're looking at the same pavement structure, you've got a stiffer material, so you've got a lower strain response, and if that strain response is lower than that fracture, you're going to get a lower amount of damage, right? So it's that combination of your fracture properties, your viscoelastic response, okay, and that pavement structure that you put it in. Okay, so if we do a different pavement structure, use a different traffic loading, okay, these things can change. Okay, so again, just something to remember when you're looking at fatigue, you've got to consider all of it. Okay, moving on to the semicircular bend test results. Okay, same type of figures here with the flexibility index values that we're showing in the top figure. Okay, so these are the actual values from the test results, and you can see, okay, those polymer modified mixtures have huge FI values. Okay, if any of you have looked at SCB results, typically any flexibility index value 10 or above is considered pretty good, and we're looking at numbers that are up around 40, okay, for these mixtures in the short-term age condition. And then you look at the bottom figure, and again, we're looking at the ratio. So you can see with the SCB, with the aging, we're getting a pretty big drop in the SCB results in terms of the flexibility index. Okay, and again, with these, okay, you're seeing the change in the aging, and you're seeing different type of behavior with those polymer modified materials than you are with the others. Okay, but still, okay, if you look at the actual flexibility index values after aging, they're still higher than a lot of the traditional mixtures. Okay, so even though you're seeing a higher drop, okay, still in the end they're better. And then finally, the DCT results. Go through these a little bit quicker. Same kind of conclusions that we're seeing here. Okay, in terms of what we're seeing for the change in aging, okay, you're not seeing as much of a change in the ratio for the DCT. Okay, at the lower testing temperatures, the fracture intermediate temperature versus the low temperature, but similar kinds of trends, okay, and again, similar kind of difference in the performance or difference in those properties that we're measuring from the polymer modified mixtures than from the regular mixtures. Okay, but still, again, even with the DCT, after aging, these are still showing to be better materials. So that's all the mixture testing, ongoing work that we're performing right now in the laboratory is looking at binder testing on extracted and recovered materials, okay, from these different mixtures. So looking at the different aging levels as well. Okay, so in terms of the 4mm DSR testing, that allows us to do the wider range in terms of the viscoelastic characterization for the different binders. Okay, so again, just an example of some of the results that we're getting. Again, the same mixture, seeing the same kind of trends that we saw with the mixture testing, okay, where the viscoelastic response of the 12-day and the 24 aging conditions are statistically similar. That 5 days is kind of at that midpoint. And we're seeing the same thing in the stiffness as well as the phase angle. Okay, we can do the same thing looking at black space, okay, looking at the Glover row parameter. So again, this is looking at a particular temperature frequency combination, so 1 point, and plotting it in terms of the complex modulus versus the phase angle, and comparing this to some of the thresholds that have been established, and look at how those materials are changing as a function of aging. Okay, so you can see again from the short-term aging, we're in that zone where we're saying, okay, we're expecting good performance from these materials, and as we age the materials, they're moving through to the point where they're beyond the thresholds that have been established for those significant cracking limits. Okay, so again, just something to start thinking about in terms of what's happening with these materials over time. Okay, so again, this is ongoing work, so we don't have a lot of conclusions in terms of the different materials as of yet. So just a summary from what we've talked about. So the complex modulus, the SCB, DCT, fracture tests, the fatigue tests, okay, as well as some of the approaches of taking those test materials, those test results, and putting them into a pavement performance evaluation and simulation, okay, can be used to track what's happening with your aging. In terms of the linear viscoelastic characteristics, okay, as expected, we're seeing the increase in stiffness and decrease in relaxation capacity, and those two long-term aging conditions, the 12 days at 95 degrees C and 135 degrees C for 24 hours, are showing similar results in terms of the viscoelastic characterization. So for your mixture, if you really want to look at just, if all you're caring about is that viscoelastic characterization, you can do the faster aging protocol. It's giving you the same results. For fracture properties and fatigue properties, okay, again, you've got to be careful what's happening with those longer term aging levels. You're getting differences in the properties that you're measuring at those two different value, or those two different conditioning procedures, and it's not consistent. Okay, we can't say that one is always more conservative than the other. It changes from mix to mix, and it's also changing whether you're looking at the fatigue approach, the fracture approach, and what test temperature you're evaluating. So really then that comes back to what's really most representative of what we see in terms of changes in the field. Okay, and that's part of what we're looking at moving into the future. Okay, so future work that's ongoing and planned is additional binder testing, looking at additional testing and analysis of cores as those materials age in the field. Okay, and the ultimate goal is to develop an aging prediction model and develop those thresholds that the DOT can use to screen their materials, but also then to do the actual performance prediction over time, okay, and do that pavement life cycle analysis, including the effect of aging. So before I move on to the next project, just a couple of acknowledgements. The two Ph.D. students that have been doing most of this work, Runha Zhang, he is the current Ph.D. student that's working on the aging project and in the middle of conducting all the binder testing. And then Rehana Rabar Rastegar, she is a Ph.D. student that graduated about 1.5 years ago, and she was the one that started on the original DOT project and started the aging project. Okay, so those two are the ones that are really responsible for most of what I showed you today. And also can't forget to acknowledge the New Hampshire DOT and contractors and other collaborators that have worked with us through this project. All right, time for a drink. So the next project that I'm going to talk about is a lot different than what I just talked about. Okay, this is something that is relatively new in terms of just thinking about what's happening with our pavements. So we're going from material testing to looking at what's happening with our pavement structures as a whole, okay? In terms of what's happening or what we should expect to happen as sea level is rising, okay? And how do we deal with it? How do we figure out how to adapt our pavement structures to those rising sea levels, especially when there's so much uncertainty in terms of what we're going to expect? Okay, so when I showed that figure at the beginning of the presentation that showed the sea level rise, and you can see that band in terms of the projections get wider and wider as you approached the end of century. Okay, so right now, in the Northeast, we're looking at projections, end of century projections, anywhere from 2 feet to over 10 feet. And that's a pretty big difference. Okay, so how do we figure out how can we be flexible, okay, to be able to adapt as we get better information on what we can expect in the future, but then to be able to adapt flexibly, okay, make sure we're not doing something now that is going to prevent or hinder potential actions in the future. So the first step in doing that is to really understand how it's all going to work. What are the implications of sea level rise on the infrastructure? So a little bit of background. A lot of the time, most commonly, when people talk about sea level rise, you're thinking mostly about surface water. Okay, so what this figure is showing is you've got a line down here, okay, that shows 1880, for example, where the sea level was and where the floodplain extended to when you're looking inland. Go forward 130 years, right? 2010 high tide, now a little bit more, okay? And so our floodplain has extended inland. Okay, now when we add storm surge on top of that, you can see the extent of where that's going to happen. Now, as we start looking into the future, okay, as we've got increased sea levels, okay, you're going to have increased storm surge, you're going to have increased surface water flooding. Okay, so that's the surface water inundation. All right, we can understand that, and then we know that there's some uncertainty with that in terms of where those levels are going to be. But one of the things that really hasn't been done is what's happening underground. So we're looking at that surface inundation, but when you've got rising sea level, you also have rising groundwater. Okay, so the way the hydraulics work is that groundwater, okay, that groundwater table has to come and match with your sea level, right? So as your sea level is rising, your groundwater is rising as well. And it's not something that's just happening immediately on the coast, okay? That extends inland, okay? And extends inland a certain amount based on the hydrologic and geologic conditions. Okay, so it's something where you might be a couple kilometers from the coast where you're thinking, yes, sea level rise, not going to be a problem because you don't get surface inundation nearly that far. But you've got sea level, you've got groundwater rising that you're not necessarily seeing, okay, unless you're paying attention to it. Okay, and that's got implications well beyond roads. Okay, we're looking specifically at the implications on roadways, but it's got a lot of implications on septic systems. Okay, in New England, we've got a lot of mostly rural, so we've got septic systems a lot of places, water supply, okay, because not only are you getting the rising groundwater table, you're getting that saltwater, freshwater interface changing. Okay, so that's a big deal. Wetland considerations. Okay, so you've got some areas that all of a sudden the wetlands are larger, which zoning, okay, that has a huge impact on that. Some areas that aren't wetlands now that'll become wetlands. Okay, hazardous waste sites, all kinds of implications. Okay, so that's what we're looking at now, is recognizing we've got sea level rise, but then projecting how is that going to impact our groundwater. Okay, now there have been studies where they've actually recorded groundwater rise. Okay, so this particular study, this was conducted in Cape Cod, okay, which is that little arm, Massachusetts, so it's not far from us in New Hampshire. And they had a well, okay, that was right near the tip, okay, in the middle of the peninsula, and they were looking at records over time. So these records go back to the 1950s, okay, and they were seeing, on average, 2.1 millimeter rise in the groundwater table, okay, over that time. If you look at the tidal gauges, okay, in the Boston area over the same time frame, okay, we're seeing a 2.5 millimeter rise in sea level rise, and then you're seeing the corresponding increase in the groundwater table. So this particular project, they went through the process of actually modeling the groundwater rise with sea level rise and established that near the coast, okay, groundwater table can be expected to rise pretty much the same level as the sea level, and as you get further inland, okay, mid-peninsula, you've got differences, so it decreases as you go further inland. And if you're near a river, adjacent to a river, which is basically another hydraulic boundary, okay, the decrease is even more, okay, because you've got that outlet for the material or for the water. So the first step in this particular project, okay, we're looking at modeling the groundwater rise, okay, in New Hampshire. So we're focusing on New Hampshire. Okay, now New Hampshire, we've got a little tiny bit of coast. Okay, so we didn't have a lot of coastline to deal with. So we're looking at the whole and coastal area of New Hampshire. So we've got a blow up here of this. So you can see there's a group of communities that are within range of the coast that's typically considered the coastal area of New Hampshire. So we looked at a groundwater model. So essentially what we did was took an existing groundwater model that was developed for a different purpose. It was really looking at drinking water, so much deeper, okay, modified it to look at what's happening nearer to the surface where we're intersecting with the pavement cross-section. Okay, so modified the existing groundwater model, which took a Ph.D. student that had significant groundwater modeling experience over a year to do. And you can see all those little black dots. Okay, those are all the observation wells that she used. Okay, so a lot of data that went into development of this groundwater model. One thing right now with the groundwater model, it is run in steady state, so we're not looking at seasonal variations yet. Okay, we will be, but this is looking at mean groundwater levels. Okay, and then we took a scenario-based approach, so looking at expected sea level rise scenarios, levels, okay, we looked at different magnitudes. So from 1 foot of sea level rise which is currently expected or projected for the year 2030, all the way out to 6 feet, worst case condition at the time we started the study for end of century. Okay, and so these are some of the results. So this is showing the groundwater rise zone. Okay, so this is showing you the areas in the coast, okay, where the groundwater is expected to rise, okay, due to sea level rise. Okay, and I think this figure is showing you, actually no, this figure is normalized as a percent. Okay, so it's not for a particular scenario, but it's showing you as a percent of sea level rise what you're going to expect in terms of rise in the groundwater table. So for the geological conditions in our coasts, okay, we're seeing groundwater rise happening up to 4 to 5 kilometers inland. Okay, pretty far. And if you looked at just the surface inundation, okay, the extent for the same scenarios are only up to 1.5 kilometers. Okay, so a lot further inland, we're seeing the effects of groundwater rise. We do see the reduction in groundwater rise near streams, okay, again, because of the hydraulics, okay, but we also see the extent of that groundwater rise is affected by geology, it's affected by the coastal geometry, it's affected by where we've got groundwater pumping that's happening, so a lot of communities have community wells, that impacts it, okay. So a lot of different conditions, so it really illustrates that to evaluate what's happening, you have to have a groundwater model for your particular region. Okay, there's not a one-size-fits-all saying, okay, if you're seeing the sea level rise, you're going to expect this much of groundwater rise. You've got to model the conditions. All right, so when we start looking at applying this to road infrastructure. Okay, our main concern is as we get rising groundwaters, that groundwater table is going to start intersecting our pavement structure. Okay, so again, we're building the pavement structure. The intent is it stays dry, right? That's the whole intent of our pavement structure. It's dry. We might have subgrade material where we've got that groundwater fluctuation, the seasonal fluctuation, but that water, except in flooding conditions, stays out of that pavement structure. Well, in areas where we've got roads that are, where the groundwater table is already close to the surface, okay, they are going to be vulnerable to groundwater rise as a result of sea level rise. And in some cases, there's pavement sections that at the higher scenarios, okay, higher sea level rise scenarios, you're actually going to have groundwater coming above the surface of the existing pavement right now. We're going to have to deal with it. So how do we identify that? First of all, identifying where those vulnerable sections of roadway are. Okay, so taking that groundwater model, overlaying the existing pavement network, the road network, okay, and then identifying which roads, okay, are in those areas of concern. Okay, so looking, and the way we define this was vulnerable roads were those that had groundwater table within 5 feet, okay, of the current pavement surface. And then looking at the different types of roads. So in this coastal area, we've got turnpike, okay, we've got statewide corridors, regional corridors, local connector roads, okay, and then local roads. And you can see in terms of just the numbers, okay, those local roads, a lot more miles of local roads that are going to be impacted, okay, which is something that the municipalities are going to have to really start thinking about. So it's not just something that has to be done at the state agency level, but a lot of times these vulnerable sections are going to be under the purview of towns and cities, okay, which don't necessarily have the resources to deal with it. The other thing that we did, so we identified all the vulnerable sections of roadway, and then we looked at several sections to do case studies. I'm just going to show you 2 of the case studies now. One is in the northern part of the coastal area, Gosling Road, and then the other one is in the southern part of it, which is Route 286. Okay, so Route 286, this is just a picture of the actual specific site that we looked at. Okay, this is a regional corridor that connects the seacoast, okay, to the main interstate, so it's an evacuation route. Okay, it's a really important roadway, especially in emergency situations. Gosling Road, this is a local road, okay, and the particular site, it's right next to where the mall is. Okay, so this has a lot of traffic, and it's not a road that's going to go away anytime soon. Okay, it's also very near. We've got an international trade port here, so there's a lot of access to the international trade port along this road. So the way we did this, we looked at a pavement evaluation, and to start off this project, we just looked at a simple layered elastic analysis. Okay, so just trying to get a feel for what's happening before we dove in a little bit deeper. So we got information from New Hampshire DOT on what the typical structures were for these 2 roadways, and then just looked at a typical truck tire, typical axle load, looked at, from the layered elastic analysis, what's the tensile strain at the bottom of the asphalt layer, what's the compressive strain at the top of the subgrade, okay, and used the typical transfer functions that are out there for relating pavement performance or number of cycles to failure for the different distress criteria. In terms of how we defined or how we modeled the saturation of those unbound layers, okay, if the material was above the water table, we used the optimum resilient modulus value. If it was below the water table, we used the saturated value from the pavement ME approach, which is basically take half of that value. Okay, again, rough estimate, okay, gives us a feel for what to expect. So from this vulnerability assessment, for Route 286, okay, you can see where the current groundwater level is, which is actually mean groundwater level is just below the level of the base, okay, and then with 1 foot and 2.7 feet of sea level rise. We didn't do the other scenarios because once you've got 5.2 feet of sea level, that section of roadway is going to be underwater. Okay, so once you get to that point, that's it. And then looking at the difference in the number of cycles for fatigue and rutting, you can see a big drop in the rutting performance of this cross-section, okay, versus the fatigue. Same thing for the Gosling Road. Okay, again, with this particular site, once we got beyond the 2.7 feet of sea level rise, got to the next highest scenario, okay, again telling us that the pavement structure is going to be underwater. For this particular pavement structure, because of the difference in the structure and the materials that are used, not as much of a difference in terms of the fatigue versus the rutting performance. So from that gives us a rough estimate. We're able to do a little bit more in terms of the adaptation planning. So knowing this, how can we modify the structure to be resistant to those changes that we're expecting? Okay, so again, the first rough approach to this, okay, was really looking at, okay, let's change layer thicknesses. Okay, so our choices are to change the base layer thickness, change the asphalt layer thickness. So looking at the combinations of different thicknesses of base and asphalt layers, evaluating the costs, okay, and determining, making sure you've got those thicknesses that are giving you the performance that you need in terms of number of cycles to failure, and the appropriate roadway elevation to make sure it's not underwater. Okay, what are the most economical solutions? Okay, so we did this for a couple of the different sites. I'll just quickly show you some of the data from the Route 286 results. Okay, and these are different pavement structures combinations, but I just wanted to show you the approach that we're using. So this is the existing condition, okay, and then this is evaluating different combinations of base and asphalt layer thicknesses, comparing those against the adaptation costs, and they were just ranked in order. Okay, so from this, you can kind of look at, okay, what are the most efficient solutions in terms of the right combination of base and asphalt layer? Okay, again, gives us an idea of what to expect in terms of how we can adapt some of those specific cross-sections to expected future conditions. Okay, so from this part of the study, we were able to identify that groundwater rise zone, identify where we had the vulnerable roads, okay, do a rough vulnerability assessment in terms of what we're expecting in terms of performance, okay, and then look at what are some possible implementable options to adapt. Okay, now, the next step, and this is some of the work that is currently going on, is recognizing that not only are we going to be dealing with sea level rise, but we've got changing weather conditions on top of that. Okay, so looking at some seasonal changes in terms of temperature, as well as those seasonal changes in terms of precipitation that we're expecting, combined with the rising sea level. Okay, and then starting to look at it not just on an average basis, but looking at changes over seasons. So one of the first things that were done was looking at the duration of the season. So we used definitions, seasonal definitions that are defined from some work that's done in Minnesota. So Minnesota DOT defines the lengths of certain seasons based on cumulative freezing indexes, okay, and thawing indexes from air temperature data. So you can see from this figure, okay, which is showing you the change in, or the length of the season, okay, as a function of annual average temperature rise. Okay, so we're not tying this to a particular time frame, but we're tying it to a change in temperature. Okay, so then that gives us the flexibility as projections change. Okay, in terms of timing, we still have the information. We can just shift it along the axis in terms of where we expect different things to happen. So for the seasons, we've got the different colors. Okay, so green is fall, red is summer. We've got two springs, okay, because we've got a spring before thaw happens in terms of the roadway and a spring after thaw happens. Okay, so we've separated those out. And then we've got winter. So as we see annual temperatures rising, our winter season, the length of our winter season decreases, and once we get to 2.5 degrees, winter, as we've defined it, or as it's defined by this approach, essentially disappears. Okay, which, again, has other implications, especially in areas of New England where they rely on frozen roads for logging. Okay, can have significant implications. Some other interesting things happen. Our fall season increases to a certain point, and then once winter disappears, the length of the fall season decreases, okay, because we've got disappearing winter. Summer season, continuous increase. Okay, with the spring seasons, that spring one, which is okay, before you've got the spring thaw, really isn't changing in terms of the length of the season. Okay, it's shifting in terms of when it's happening during the calendar year, but the actual length of time isn't changing. Okay, we are seeing some changes in that thaw period, though. Okay, not as dramatic as the fall and winter. So what does that have in terms of an impact on the amount of damage? Okay, so what we're seeing then is if we look at the fatigue damage that is accumulated and the rutting damage that is accumulating, okay, over the course of a year, it's starting to happen at different times. Okay, so typically we're used to thinking about most of our rutting damage is happening in the summer, right? And not a lot is happening other times of the year. But as we're getting these changes in the length of the season, you're seeing that in terms of proportionally, okay, and again, same colors here, less of that rutting damage is happening during the summer, and we're getting more of it during the fall and the spring. Something to think about. Okay, same with fatigue. It's not changing as much with the fatigue, okay, but you are seeing changes in the relative proportion of when you're getting that damage happening. Okay, and again, this is for a particular case site, so this is using that 286 regional corridor. So then once you've got this information, okay, you can look at how to change, again, those granular base layer thicknesses and the asphalt layer thicknesses. Okay, so the way this analysis was done is a little bit different than we did it initially. Okay, now we're looking at what are the required thicknesses to maintain a certain level of reliability in our pavement design over time. Again, considering the combined effects of temperature and the sea level rise. Okay, so this first graph is showing you the required asphalt layer thickness, okay, assuming a certain thickness of base. Okay, so in terms of adaptation, all you're doing is adding additional asphalt on top. Okay, and then again, this is plotted as a function of annual average temperature rise. On top of that, the different boxes show the different scenarios that we're looking at in terms of future climate. Okay, so the blue blocks, this is early century, so this is what we're expecting in the next 5 to 10 years, all the way up to the red box, which is what we're expecting late to mid-century. Okay, and the boxes have that width. You can see they get wider and wider as we get further out because the uncertainty increases. Okay, so we've got the variability in terms of the thickness, okay, from that uncertainty, and then also the box becomes wider because we don't know exactly where those are going to end up. And then on the bottom one, okay, what we've done is we've fixed the asphalt layer thickness, okay, and looked at what's the granular base layer that we need. Okay, so looking at it from two different perspectives in terms of your adaptation alternatives. Okay, and same kind of thing, you can see how much thicker it needs to be. So taking all this information, then we're taking it and looking at how do we design a framework or an approach, okay, to design a climate-ready road to be flexible. Okay, so we want to make sure it's an approach that can be staged. Okay, so you don't necessarily have to take an action now for something that you expect to be a condition 50 years in the future, but making sure that whatever you do now doesn't hinder your ability to further adapt in the future. Okay, and again, looking at the combined effects. Okay, so again, just a reminder of what we're looking at. Okay, as the groundwater moves into the underlying layers, okay, you've got increase in temperature on top of that. You're expecting more fatigue cracking and more rutting. Okay, so we're looking at developing that framework for coastal road infrastructure, okay, and making sure we're adaptable to those changing conditions. Okay, and the approach that was used is a hybrid between two different types of approaches for adaptation, a top-down and a bottom-up approach. Okay, and we're using a hybrid approach in this study. So typical bottom-up approach, you've got stakeholders and you're looking at different adaptation alternatives, and you're identifying those different alternatives, doing the analysis, and then identifying which is the optimal one. Okay, that's the bottom-up approach. The top-down approach, you're looking at what are your future scenarios, okay, and coming from that perspective in terms of choosing the appropriate scenarios to evaluate with some stakeholder input, and then assess your different options. Okay, so again, we're combining these two approaches. Okay, so the methodology, first of all, very important to involve stakeholders. Okay, so it's not just engineers, pavement engineers sitting in a room making decisions. Okay, it's involving everybody from the municipal level, decision makers, all in this, because it has to be something that decision makers are on board with. Identifying what those adaptation alternatives are, defining what the performance metrics are, okay, and then choosing your models that you're going to use. And then the idea then is to develop what's called a climate sensitivity catalog. Okay, so you can see how sensitive your material or your structure is to those different changing parameters. So how sensitive is it to sea level rise? How sensitive is it to temperature change? Okay, so this is an example of what a pavement climate sensitivity catalog would look like. Okay, so what we've got here is for different pavement structures. Okay, so in the upper left corner, okay, we've got a fixed gravel base of 406 millimeters. We've got groundwater rise, okay, so going from 0, no change in groundwater level, okay, up to 0.7 meters. Okay, and then on the horizontal axis, we've got the change in temperature. Okay, so looking at the combination of temperature change and groundwater change, okay, 4 different pavement structures. And what these show, the numbers in here, are the required thickness of your asphalt layer to maintain 85% reliability in terms of performance. Okay, so this is just showing 4 different cases where we've got 4 different gravel base thicknesses. This one's the relatively thin, 406 millimeters. Down on the lower right, we've got the thicker 711 millimeters. Okay, and then these are shaded in terms of the thickness. The closer, the deeper red color is the thicker asphalt layer. The lighter green or the darker green color is the thinner asphalt layer. So this gives you an idea of how sensitive your pavement structure is to those relative changes in temperature and groundwater rise, but also very clearly shows you that if you've got a thicker gravel base, you've got a much more flexible structure in terms of what you need to add for asphalt. Okay, and again, important to note, this analysis is based on one specific site at this point. Okay, so these aren't global numbers. So once you've got that information, so now you know how sensitive your pavement structure is to changes in temperature and groundwater. Okay, now we've got an overlay on that. Okay, what are the different climate change scenarios you're interested in evaluating? Okay, and use that output to figure out what's the timing of any of those particular combinations of groundwater rise and temperature rise. Okay, so once we know the sensitivity, then we can figure out the timing and we can figure out what are the most likely scenarios potentially to happen. And then we can figure out what are our adaptation alternatives. And you can think about what's called an adaptation pathway, okay, in terms of this is the action that should be taken now versus this is action that you should think about in 10 years from now, 20 years from now. Okay? And you can change different adaptation pathways depending on how things change in the future. Because as we get further on in the future, we'll have better estimates, less uncertainty in terms of what we're expecting for future conditions. Okay? And in that way, you can recommend that stage adaptation plan that allows you to be flexible. So for this particular study, again, several different climate change scenarios that we're looking at. And then this figure just gives you an idea of what those projected average temperatures are going to be. Okay, so how much we're expecting the temperature to rise, okay, and how that changes through the year for the different scenarios. All right, now looking at some of the results. Okay, so again, we're looking at different gravel-based thicknesses to start with, and looking at how that asphalt layer thickness, or the required asphalt layer thickness to maintain that 85% reliability, changes as a function of time for the different scenarios. So we've got time now on the x-axis, okay, and the different lines represent the different climate change scenarios. Okay, and what's interesting, regardless of which gravel-based thickness, okay, for the near term, basically doesn't matter which scenario you're looking at. It's giving you the same information in terms of the recommendation for the thickness you need for your asphalt layer. It's not until we get out to about year 2040 that things start to diverge. Okay, so really it doesn't matter which scenario you're planning for right now, same recommendation across the board. But as you get out further in time, okay, then things start to change. Okay, and again, this is just a different way of showing some of the similar information, is showing it in a graphical format, okay, in terms of the thickness of the asphalt layer that you need as we march on in time, and this is showing you how the groundwater table is changing again over the time. So you can see that 2040, okay, that's where we really start to see more of the bigger impact from the groundwater rise. All right, getting close to the end. So just some of the conclusions from this work, again, that is still ongoing, is really looking at comparing present value costs, okay, for all of those different the reasonable adaptation pathways, okay, for each of the different scenarios, and using that to identify what are the most cost-effective and robust and flexible options to adapt to what we're expecting for changing climate in the future and sea level rise. Okay, so using this stepwise approach, okay, allows you to reevaluate things over time. Okay, so once that climate sensitivity analysis is done, it doesn't have to be done again. Okay, you just have to revise what the time frame is. Okay, and that's one of the advantages of this approach. You're not consistently have to redo the analysis. You do that analysis, and then as time goes, you can refine what years are associated with that analysis. Okay, and then again, knowing that you don't want to take those actions that are going to preclude future actions that could be beneficial. So the acknowledgements for this work, this is done by a Ph.D. student, Jane Knott, okay, and a lot of support has come through ICNet, okay, and funding for some of this work comes from New Hampshire Sea Grant, New Hampshire DES, and National Science Foundation, again, so acknowledging the funding sources and the various collaborators for this work. And then the last slide, thank you for all your attention. And I showed you early on what UNH looks like in the fall. This year, again, changing climate, went straight into winter. So this is what campus looks like. We got about 6 to 8 inches of snow on Friday before I left, and I'm getting warnings on my email saying that there's more snow coming for tomorrow. So thank you for the opportunity to be somewhere a little bit warmer for a couple days.
You have a question regarding the fatigue test, regarding the aging protocol. What is the one that you prefer right now among the values that you show?
Good question.
We are still using the 5 days at 85 degrees C.
The 85 degrees C, that was part of the first part of the project, and we've essentially dropped that, preferring the loose mix protocol for avoiding the differences in aging gradient among the different samples because we're looking at different sizes of samples for the different tests, and so we want to make sure we've got the consistent gradient throughout. So we're not doing the compacted mixture aging anymore. We're just moving forward with the loose mix aging. In terms of looking at the different temperatures, based on what we've seen, it looks like there's definitely differences in those aging temperatures, and we're reserving judgment on which one is better until we get some more of the field data. Because there's the difference, again, for viscoelastic characterization, you can do either one. But when you're looking at the fracture characterization, we want to make sure we're really representing what's happening in the field. And right now, that's an open question, because we just don't have enough of the field data, the actual field aging results, to be able to make that assessment.
Okay, what about delta TC and the global ROE and the R value?
So the delta TC for the binder perspective, okay, does appear to be a really good screening tool. It has screened the mixtures or the materials, I should say, the binders that we know are problematic. Okay, so it did identify those. But there's a challenge there when you're using a binder parameter, and really what we're looking at is mixture performance, especially when we're talking about recycled materials and we start adding in rejuvenating agents and things where they're impacting the mix, but then once you extract and recover the binder, it's a different effect. So I didn't present it here, but a lot of work that we've currently got ongoing is looking at a mixture version of the Glover row parameter. Okay, so instead of just looking at the binder Glover row, we're looking at mixture viscoelastic characterization to see if we can use that as a screening tool. Okay, and again, it's mostly a screening tool because you're just looking at viscoelastic characterization. You're not looking at the fracture or fatigue properties. Okay, but that's currently ongoing work.
I saw something about that in Brazil with Asian.
Yep, you did.
Okay. I have another question regarding I forgot, thinking in Asian, I forgot my other question. Regarding the second presentation that you made, you are only studying the saturation change in the granular materials, not for example, the effects of the salts for example, in the HMA performance.
So no, we haven't done any of that yet. And
Okay.
the other thing, I didn't mention it during the study or during the presentation, that initial adaptation analysis that we did where I talked about the resilient modulus above the groundwater table, just at optimum, below the groundwater table, we're saying is half in terms of the resilient modulus value. In the advanced analysis, so in the seasonal variation, we're also looking at the approach. We were able to break down the unbound layers that are above the groundwater table, okay, into different sublayers that had different saturation levels. So we're accounting for some gradient in saturation. Okay, so we've got partial saturation above the groundwater table. So we did do that advanced analysis, or finer resolution, I should say, really, in terms of divvying up those unbound layers in terms of the resilient modulus values based on gradients, saturation gradients.
What was the software that you used to do all those modeling?
What
software do you use?
The software for that second part, we're using the MinPave program. Okay, so it's the Minnesota DOT mechanistic empirical approach. And so that allows you to do the seasonal variation. It also allows us to break down the pavement structure into the different sublayers and account for those different saturation levels as a function of season as well. So that's how we're able to say, okay, so much is happening, damage is happening during different seasons. So that's the software that we're using.
Okay, pretty good. Thank you.
And it's freely available, which is nice.
Yeah, okay, pretty good.
Sure.
You used the 24-hour loose mix at the 135, and that's some work that was done. But at AI, but they had also done 12 hours at 135 to give you sort of an intermediate. And when I looked at the data you had there, you know, the 24 hours was, you know, equivalent to your 10 days.
Yeah.
But it almost looked like if you had gone with the 12 hours at 135, you probably would have been in the middle back. And
Close to the
12
5
hours
days.
is a lot better than 5 days.
Oh, absolutely. There's no question about it. So there's the balance between what represents what's happening in the field and the practicality. And in terms of, we selected that 24 hours. Again, it's a laboratory experimental program. We had to make some decisions on the different conditions that we were testing. We chose the 24 as an extreme condition. We chose the 12 days based on the current, at the time when we started the project, approximate recommendation from the NCHRP in terms of what New Hampshire conditions would be. And then we chose the 5 days to be somewhere, we guessed, close to the middle. Okay, so that was the rationale. Now, as we move forward, okay, and start to develop this a little bit more, we're dropping some of those, okay, and focusing on some of the other different aging levels. But yeah, the question of the different temperatures, it's a good question, and really, you know, what it comes down to is which one really simulates or does a better job of representing what's happening in the field.
Close enough.
Well, yeah, but how close is close enough?
We have had studies extracted asphalts with the normal asphalts because there are differences in the processing. We have a lot of differences, solvents, interactions with the asphalt, vapor. When you separate the solvent from the asphalt, you can separate some other things, and the content remaining, even some Glover Road tests are based on extracted asphalts. Do you think this would be that would make the difference in this type of analysis?
Yeah, like I mentioned, evaluating the binders versus evaluating the mixtures. When we're looking at these different materials, and we've got the complication of the solvents, we've got the process of extraction and recovering the material, fully blending recycled materials with the virgin materials, which doesn't necessarily happen to the same level in the mixtures. The binder testing does have the disadvantages. There's a limitation to what you can get from that type of analysis approach, which is exactly why we're looking at doing the mixture Glover row, so looking at really the mixture response from the viscoelastic perspective, as well as recognizing that it's just not a viscoelastic response in terms of the damage in the field, but you've got to look at what's happening once the material gets to that damage state. Okay, and I think that the similarities that we're seeing in those aging protocols, where it's the same on the viscoelastic response, but once you get to a fracture or fatigue response, it's different. Okay, that tells you that there's something else going on once we start to damage that material that we've got to somehow account for. Okay, so really looking at, if we're looking at the performance of the mixture, then we gotta test the mixture. Okay, and there's challenges with that. It's not as easy to do, but that's the direction we feel strongly that we need to move.
The second thing, you show a very interesting result. We have a research project here. It was very similar with pure binder. This is associated to the modulus. The higher the modulus, more susceptible to fatigue. We did 5 PAV, and we failed it in controlled stress. First cycle, second cycle, the modulus went up, and fatigue strength went up to the third cycle. After the fourth cycle, strength drops. So we realize you have to deal with the modulus and energy dissipation. And your results are very similar to what we saw with our pure binders here in the lab.
That's interesting, seeing the similar results, and I agree, you've got to look at more than just that viscoelastic response. Okay, so looking at overall, you can think of it in terms of the energy dissipation, you can think of it in terms of the fracture or fatigue properties of the mixture, but we agree it's important to look at that, and then also additionally, the work that I showed in terms of the pavement structure. So not just looking at the mixture characteristics themselves in isolation, but also considering how that mixture is going to perform in different structures. Because you might have a material that's great as a surface mix, okay? A different type of mixture, different formulation, different materials that are going to be much more effective as a layer lower in the pavement structure. It's all important to consider. That's what makes this fun, right?
¿Alguna otra pregunta? ¿Sergio? No. Pensé que estaba levantando la mano.
Have you considered using other mechanisms in the aging protocol, like UV radiation? Because we have observed when analyzing samples subjected to the field that the aging mechanism is slightly different when you have radiation or other elements. So I don't know if it's something that you're thinking for the future or.
Definitely considered. Haven't had the opportunity to look at it yet.
When you asked that, yeah, I've done that work, and several other people have also looked at. And what we find, and one thing they use a weatherometer, which is a device used for roofing. And so you add UV light plus temperature plus moisture, and we've aged samples using that. And the one thing that you see different is that that UV penetration, it does a significant amount of aging to the asphalt mixtures. That we've seen that taking samples from the roadway, but that aging that's done by the UV is just in the top 4 or 5 millimeters. As soon as you go below that, then you don't see the effect, because the UV doesn't penetrate down any deeper than that. But it does have a major effect, because that is where, for example, your top-down cracking starts, is right at the surface. And so if you have a much more brittle, stiff material right at the very, very top, you'll start to see the problem. And so there's been work on taking the individual layers, say every about 10 millimeter sections of the pavement, and you'll see very dramatic changes as in that first 10, 20 millimeters compared to the rest of the layers. So, but we have looked at aging the specimens, and you see the same thing, because you put the UV light and it only hits the top of the specimen, and so the penetration is only just very narrow, where the inside then just is more affected by the actual temperature and oxidation.
Yeah, and we've done some similar work looking at that aging gradient, extracted recovered binders, and also, to the extent we can, with mixture specimens that we can take different depths, and same kind of thing. There's definitely the gradient that we're seeing. Thank you.
Y bueno, quiero agradecerles a todos, a nombre de LanammeUCR, por su participación en este seminario de hoy día. Rápidamente, para retomar lo que hemos hablado, si ustedes le ponen atención, las presentaciones han tenido una secuencia, no han sido No fue un orden aleatorio, ni los temas tampoco, ni los especialistas que hemos traído los escogimos aleatoriamente. Fue pensado por varios meses para tener a profesores como los que hemos tenido hoy. Se necesitan muchos meses de antelación para preparar un evento como este. Les estoy hablando de mínimo casi que un año de tiempo de planeación. Si ustedes ven los temas, todos tienen que ver o están altamente relacionados con investigación que estamos haciendo actualmente en algunas de las áreas de laboratorio. Particularmente, por ejemplo, el tema de diseño balanceado de mezclas asfálticas lo hemos empezado a analizar con la unidad de auditoría técnica y con la unidad de materiales y pavimentos fuertemente. Precisamente acaba de salir una auditoría técnica muy extensa con datos de fatiga y de deformación permanente de todas las plantas asfálticas de Costa Rica, donde si bien es cierto no culminamos el análisis de diseño de mezcla balanceado, tenemos absolutamente todos los datos para entender en campo cómo varían las mezclas en Costa Rica respecto de estos parámetros y eventualmente llegar a sugerir una especificación para diseño de mezcla que complemente ya las especificaciones que tenemos de fatiga y de deformación permanente que actualmente están vigentes para los proyectos de obra nueva y para los proyectos de mantenimiento. Esto es algo muy bueno y por eso la presentación inicial del doctor D'Angelo. Después, la presentación de Gordon, hablando de un tema que tal vez no sea tan conocido, pero donde sí hemos publicado bastante, que es el tema de energía de tensión superficial libre, que igual lo es. ¿Por qué nos metimos en ese campo? Básicamente por el tema del daño por humedad. Estamos trabajando fuertemente en el tema de daño por humedad. Y cuando me tocó hacer el doctorado, antes de venirme, llevé un seminario y ahí fue la primera vez que conocimos el goniómetro. Después con el tiempo lo compramos en el LanamME y ahora, bueno, particularmente la química Alejandra Valdí tiene varios años de haber tomado esa investigación y la hemos presentado en varios lugares, en Europa, en Estados Unidos, y hemos empezado a obtener algunos resultados, tanto así que emulando a Texas estamos sugiriendo ya un borrador de especificación de energía de tensión superficial libre para agregados, que presentamos a la Comisión de Normativa Interna de la LanamME hace cuánto, José Pablo, un par de meses, precisamente para no quedarnos solo en la investigación, sino poder llevar eso a mezclas que resistan mejor el daño por humedad. Eso es parte de lo que estamos haciendo y por supuesto todos los temas, los otros temas de mezclas que se autocuran, muy interesantes, que en eso sí no hemos trabajado mucho nosotros, pero sabemos que en Europa hay un gran desarrollo. Debo mencionarlo también que una exalumna nuestra y compañera de la LanamME, Paulina Leiva, actualmente está haciendo su doctorado como parte de este proyecto que Gordon nos enseñó, el SMARTY. Empezó, bueno, lo conocen hace un año y está trabajando precisamente en materiales mecanomutables, que es como se le llama en España, en la Universidad de Granada con nuestros amigos Maika y Fernando, que precisamente el año entrante tienen el ITA. Entonces estamos muy contentos de saber que Paulina es parte de este proyecto SMARTY, que como vieron es un proyecto muy importante en Europa en este momento. Y luego finalmente la presentación que dio la doctora Daniel, Joe, muy importante por dos temas. Ustedes saben que desde hace casi 2 años la unidad de sostenibilidad empezó a trabajar el 1 de febrero del año 2017. Hemos estado trabajando en huella de carbono y eventualmente vamos a entrar en los efectos del cambio climático sobre las propiedades de nuestros pavimentos. Indudablemente, como decía ahora Joe, hay un cambio climático, es latente. Nosotros nunca habíamos tenido un huracán, el último huracán que había impactado Costa Rica había sido en 1863, lo sé bien porque tengo una hermana que es doctora en meteorología, recién graduada, y ella hace algunos años me pasó cuál fue el trazado de ese huracán, y habitualmente ustedes saben que los huracanes se van hacia arriba y últimamente han estado empezando a pegar más hacia abajo en la región centroamericana, en la región de las islas del Caribe también, bueno, que ahí antes pegaban, pero la frecuencia ha aumentado. Entonces sí tenemos un efecto en el cambio climático que es algo de lo que queremos evaluar en el HVS, en las pistas a escala real, de ver precisamente cómo variando la saturación de los materiales, haciendo saturación parcial de los granulares y de los materiales granulares, perdón, eso va a afectar el desempeño del pavimento y así el diseño de pavimentos que hacemos. Eso es muy, muy interesante. Indudablemente la primera presentación que dio Daniel hoy acerca de de RAP, bueno, nosotros no tenemos el RAS, que son las tejas recicladas de asfalto, pero sí queremos entrar más fuerte en RAP, así como lo hemos hecho en plástico. Ya precisamente ahorita tenemos un proyecto de investigación muy grande para implementar el uso de RAP en mezclas asfálticas municipales, para arrancar por municipios. Y esos parámetros, precisamente los parámetros de fractura, los otros que conversamos, el delta TC, el global ROWI, el R-value, son factores fundamentales para entender cuál va a ser el desempeño futuro de estas tecnologías. Y eso es muy importante. Ya los tramos experimentales con RAP ahorita se empiezan a construir. Ya se construyó uno de 1 kilómetro en Escazú. Y los que nos siguen en Facebook saben que la semana pasada construimos la primera mezcla con asfalto modificado con plástico en Panamá. Entonces, vamos hacia eso, pero lo ideal es tener parámetros de análisis en laboratorio que de previo nos digan cuál va a ser el desempeño in situ. No queremos fallar en esas tecnologías, muchos de ustedes lo recuerdan, yo sé que don Mario Arce particularmente lo recuerda, tal vez don Víctor Cervantes se acuerde, el famoso reciclado en caliente in situ que tuvimos en el 2001, que desgraciadamente falló radicalmente y han pasado 17 años y no volvimos a reciclar pavimentos en Costa Rica. Entonces tenemos que volver porque es necesario por el tema de la sostenibilidad. De nuevo volvemos al tema de pavimentos sostenibles y resilientes, que no fue una locura que se nos ocurrió, lo hicimos y cuando iniciamos la unidad de resiliencia y sostenibilidad en el LanammeUCR fue precisamente pensando en que necesitábamos un grupo experto en ese tema que complementara desde cálculos de huella de carbono hasta todos estos temas. Ahorita las muchachas van a tener que entrar en diseño de pavimentos muy fuerte también y diseño de materiales, porque todo esto lo estamos viendo que necesita ser aplicado también. Y me alegra mucho ver que están aquí también en todo este evento. Agradecemos mucho a los amigos de la industria que han venido, a los amigos del gobierno, nos honra mucho tener aquí a doña Eliana Aguilar, que ha sido colega de muchos años, pero es la presidenta del Colegio Federado de Ingenieros y Arquitectos. Entonces estamos muy contentos de que hayan participado en este día y bueno, seguimos adelante con todos estos temas de implementación tecnológica. Muchas gracias a todos, así nos quedamos despedidos. Muchas gracias.